Hi everyone, I'm really pleased to introduce Clayton. So Clayton is a research scientist at Google, and he did his PhD in Columbia, where he worked on, among the other things, he did some great work on the explicitity and complexity of complex neural networks that we're going to hear about today. And he is also a Brown alumnus, so I'm really happy that he's able to come back here and give this talk.
Great. Thank you very much for the introduction, Alessio, and thank you all for having me. It's always very fun to come back to Providence, especially with the fall colors like this, and especially with so many of my teachers and mentors in the room. I took classes from Ellie and Anna and Carly, and TA'd for Carly and Anna, and did research with Ellie, so it's really a privilege to be here with you all and to get to talk about my research with everyone. So the rough idea of this talk, and I want this to be ideally interactive, is I want to talk about theoretical toolkits for understanding large language models. So like this distributed computing thing is in here because like this is a particular framework that we're going to use to understand what language models can and can't do. But really what my goal with this talk is to try to kind of have a dialogue between theorists and machine learning people to try to figure out like what is a good theoretical toolkit we can develop for thinking about modern language models and for like, either proving good theorems or designing rigorous experiments that give us interesting properties. So my goal is that we'll have some good question and answers, that we'll talk about different ideas, and also that like, people come out with an understanding of what language models are, what transformers are, and what types of theoretical questions you might ask about them. So maybe before I jump in, I just want to ask a little bit for the people in the room about just like roughly what backgrounds people have. So maybe can we do a show of hands for undergrads in the room? Cool. And how about master's and PhD students? A lot of people. And then postdocs? Cool. And I think I know who the faculty members are, but just in case. And are most people in the computer science department? Okay. Applied math? Okay, some good APMA representation. I was APMA CS myself, so a balance. Anyone else? Other departments? Yeah?
From Cog-Sci department.
Cog-Sci, cool. Physics? Nice.
Neuroscience.
What's that?
Neuroscience.
Neuroscience. Okay, cool. So we got a good variety of people here. So yeah, let me jump in. Why is this not? There we go. So what we're trying to do is we're trying to understand how neural networks work. And there are several different tools you use to do that. And one of the main questions you ask about is expressivity, which basically is a question of, I have some family of neural networks, which I can think of as like a parameterized mathematical function. And I'm asking what types of computations or mathematical functions can I compute with this parameterized family of functions. So the quintessential result you may know about, if you've heard anything about neural network expressivity, is what's called the universal approximation theorem, which basically says that if I have any mathematical function, there exists a sufficiently large neural network that will closely approximate it. So, I'm given some function from Rd to R, I'm given some domain that it's over, and then I can tell you that there exists not only any neural network, but specifically a two-layer neural network, where I have linear units apply non-linearity, and then I have another linear unit on top that will closely approximate it. So this at first glance seems like a very cool and exciting result because it tells us that there's effectively no limits to what we can learn with neural networks. But of course, when you look at what types of things people are doing in practice, they're not training these shallow, very simplistic two-layer models. They're training more complex stuff. So this gives rise to like a somewhat more recent strand of results that then tries to prove separations. So this family of theoretical results would say something like, okay, I know you could represent anything using an extremely wide and extremely large two-layer neural network, but there are some times when depth helps you. So this paper by Eldon and Shamir in 2015 says, I'm going to give you a specific function that benefits from depth. So I can give you a three-layer neural network that's going to closely approximate it, and it's going to be polynomial size, and any two-layer neural network that will approximate it is going to have exponential size. So like this is kind of a quintessential result, which like if you were looking at the neural network expressivity theory literature 5 to 10 years ago, you'd expect to see. And the key toolkit you'd use for this is functional analysis. So if you're familiar with like using Fourier expansions or like Boolean function analysis, depending on your domain, you decompose these functions in certain ways, and then you relate those to neural networks. So you have this toolkit that was able to give you architectural trade-offs. But machine learning has changed a bit in the last 5 years or so. We have this whole LLM craze. We have these new transformer models, which I'll talk a lot about in this talk. And there have kind of been a few paradigm shifts that I think are worth accounting for when we talk about what makes a good theory of modern machine learning models. So one of the factors, which again I'll come back to a number of times during the talk, is the emergence of this transformer architecture instead of the standard feed-forward neural network that I talked about in the previous slide. And that kind of initially took over language models and then took over a bunch of other different types of machine learning models. So you have this architectural shift. You have a shift towards like sequential modeling tasks, where like if you use ChatGPT, what you're doing is you're entering a bunch of text in, and you're asking it to infer what the next text, what you're asking it to answer a question, or to generate more text, or to summarize text. But the key thing is you can import a very large amount of information, and there's some sequential quality to it. Like the words come in an order, and you can also frame. There are a lot of problems you can frame this way. Like you could supply a Go board as a sequence of inputs or something like that. And typically one of the critical things here, which is kind of different than the previous regime, is that the sequence length might be very large. Like the company I work for has new machine learning models where you're supposed to be able to enter in up to like 1 million words and do inference based on that. So like that's a very long number of words, a much larger input size than before. And when we're thinking about theory, this might mean we might want to parameterize the problem differently, or we might want to think about different trade-offs. And then kind of hand in hand with that, there's also this idea that like the core thing you're doing is you're trying to predict the next token. So I give you a collection of words, and I'm asking you, given the words you've seen so far, what word comes next? And this is mostly what we're training a lot of these LLMs to do, and that's kind of different than the paradigm reflected in the previous slide, where you're just like learning a mapping from some vector to a different vector or real number. And then also you have a number of different ways in which you interact with the language models. Maybe you train a language model from scratch, which kind of evokes how we would normally do machine learning. Maybe you take a model that was already trained for something and then tweak the weights a little bit. Or maybe you take a fixed model and just try to cleverly prompt it and like ask it questions without ever changing the underlying weights. Yeah?
In that company you work for,
yes.
I would think that the embedding dimension would be huge and much larger than the sequence length, in fact. But that's not what you're saying here.
That's not what I'm saying here. I can't say too much about what the company I work for is doing, but I can say that
public model.
Yeah, I can say if you
is much bigger, right? In the sense that if you consider the embedding dimension to be the number of neurons.
So it depends on how you count things, but typically, like if you look at like I think GPT-3, I think you're thinking n is like 32,000 and m is like 2,000 or something, and that's the embedding dimension per token. So what I'm saying is like I give you a list of words, I map each word to an m-dimensional encoding.
So you don't think about I shouldn't think about it as the activation level of all the neurons in the model.
No, we're not thinking about that right now. We're just thinking about like the size of the input embeddings, basically. Like the main point is that the dominant quality is not the size of the embedding dimension, but the number of embeddings that you're getting in.
Embedding. Okay, there's another notion of embedding, not the.
Right. Yeah. There's a million embeddings. It's a mess. but thank you. Good clarifying question. And I guess like the exciting thing kind of about this is we have all these different kind of changes in assumption, and we have like a pretty wide open theoretical space. Like as I'll talk about more more later on in the talk, there's a lot of different kind of more diverse theoretical tools that are being applied to this, some of which are developed in the papers referenced herein, but others which are completely orthogonal and taking it in other directions. And I think because you have this kind of like rush of new you have this paradigm shift, you also have a rush to define like what are the right assumptions when doing theory, and what are the right types of like results we should import in from other areas of theoretical computer science. So what is this talk going to look like? Well, what I'll first do is I'll first talk about what a transformer is, and I'll try to like go through in relatively fine-grained detail what kind of I'm thinking like the key architectural features are of that. I'm going to talk about a model of distributed computing called massively parallel computation. I'm going to talk about a relationship between transformers and massively parallel computation, and then I'll talk a little bit about what that tells us for what algorithms you can solve using a transformer. And then at the end, I'll talk a little bit about empirics just to validate that it's not a totally unhinged, crazy theoretical thing, that there's at least a little bit of grounding to it. So that's roughly how this will go. Any other questions before I jump into a little more of the technical content?
Yeah.
Yes.
A couple slides ago, you were comparing N and M, right?
Yeah.
So the number of tokens and the dimension of each representation. Why did you make that comparison specifically? Like, should we desire a larger M to like express more related to like attending to many things, or?
So the reason why I drew that attention or drew attention to that is because having bounded M imposes additional restrictions on what types of things you can express using the architecture. So these are kind of like restrictions that we have been able to do just fine with, and possibly inductive biases that are helpful for training models like this. So I think, you could definitely think in terms of a larger M, but like for the theoretical regime we're thinking of here, it's useful to like ask, okay, what follows if we assume that like this N is scaling faster than this M? There are other papers that look at different scaling regimes, and that's, I think part of the exciting thing about being in this time for this field. Cool. So what is a transformer? So transformers, kind of as I mentioned before, is sequence-to-sequence architecture. I give you in a list of words, and you're going to think of that as mapping to another list of words. Very often the list of words you output will be the next word in the sequence, but not necessarily. You could just have like a list of tokens, and you map that to a list of other tokens. But the key thing is you want to think about like the sequential input and the sequential output. Transformers, as I mentioned before, are have effectively been the backbone of large language models. They're introduced in 2017, and they quickly replaced other architectures, such as especially recurrent architectures for natural language processing, and like have pretty much they are now almost exclusively the state of the art. And they've also done quite well in other domains, so including like vision domains and things where like you don't necessarily think of them as like an intrinsically sequential domain. They still do quite well. And there's a few like useful features of transformers to think about. One is like they tend to be good for parallel hardware in a way that recurrent networks aren't. So there's like kind of a practical hardware reason for doing them beyond whatever inductive biases or learnability properties they have. They work better on TPUs and GPUs. The core primitive, which I'll get to in a minute, is these self-attention units, which are associative rather than recurrent, which I'll mention what that means in a minute, but that's like a very key thing for understanding transformers. They scale to long context lengths, like I mentioned, the 1 million plus for Google. And critically, they have this big computational bottleneck where like, if you're going to use this architecture, you're going to end up having to compute some n by n size matrix, and that is very uncomputationally friendly. And there are a lot of approaches out there that are trying to figure out how do we do this more efficiently. And part of what I'm going to try to do in this talk is to respond to a few of those and mention that at least for certain types of tasks, you lose something fundamental when you try to approximate it. So let me break down what the transformer is. So we're going to think about this as a sequence-to-sequence model. So specifically, let me think about the input being a matrix X, which is going to be shape n by d. So I'm going to think of that as a collection of n embeddings of dimension d, one embedding per word, say. And the transformer is going to be some parameterized function that maps that to a different, also n by d dimensional output. The core unit is this attention head, which is also going to be a sequence-to-sequence function. And the critical thing is that basically, the idea is it's associative. So you are learning some row stochastic matrix, which says how much affinity does each element have to a different one, and then it computes some inner product based on that. So what does that mean? Well, specifically, you're going to have the input, and you transform it to make 3 different types of vectors. So you have what we call a query, a key, and a value. And we can think of these as being some low-rank matrices. And then what we do is we're going to multiply the key times the query matrix together and pass that through this softmax operation in order to get an n by n matrix. And critically, that n by n matrix is going to be row stochastic, which means all of the entries are between 0 and 1, and each row adds up to 1. So in effect, you can think about each row of this being a probability distribution over other inputs. So what I might have is like, and then you multiply that by the value vectors. So what this kind of intuitively means is that we're learning kind of it's almost like an information flow, where you have values, and based on the cells that are the large cells, that's how you decide which embeddings to retrieve. So for instance, you might have a matrix where the way these vectors work out is that it'll be the diagonal matrix shifted 1 to the left. which then means it's going to correspond to a unit that copies the previous embedding up to the next token. So like it's very easy for parameterizing relationships like that. And the key thing is basically any low rank matrix passed through the softmax is going to give you something of this form. So you have one of these attention units. And then what we do is then we build up from there. So first you're going to have several of these happening in parallel, each with their own parameters. So we're going to have what we call H heads of attention. And then we're going to iterate these multiple heads over different layers. So what we'll do in between is we're going to interleave these attention units with multi-layer perceptrons, which we can think of as just standard neural networks, but the key restriction is that they only apply to single elements. So like you have some function that applies to each xi, and then what we do is then we interleave them. So you have a layer of attention, and then you have a layer of MLPs, and you iterate that. And the rough mental model you can think about is that I give you a collection of embeddings, and they're allowed to do computation to themselves in the MLPs, but they're allowed to communicate with different embeddings in the attention layers. So like there's kind of this segmentation into these two different parts of the architecture that you're able to do depending on how it's set up.
Okay, so I'm lost. So
Yeah.
This is a pipeline. Just give me an idea of the dimension of it. What's flowing through this? Is it still something of a matrix, an X by D matrix?
Yeah. So if you think about like the output of each being some like roughly X by D matrix.
Where D is some fixed. That D is the dimension of your embedding.
Of the embedding, yeah. So you're applying a series of transforms to that sequence.
And the rows of this matrix, at least at the input, correspond to they form a sequence? The order of the rows is significant.
The order of the rows is significant. You could think of them as like a collection of words that have an order. And then you have the MLPs are like computation on each unit, or on each embedding. And then the attention units are how they can is when you have this like softmax matrix and they're able to send information back and forth. Anna?
What is softmax?
Oh yes, softmax is. We don't have a whiteboard.
We do.
Oh, we do?
There's just no room for it.
Okay, yeah, it's just all covered up by screen. The softmax is basically like you map a sequence of numbers to a row stochastic to a probability distribution, and the way you do that is you take the exponent of all of them and then divide it by the sum of the exponents. So that way you're like mapping each thing to a positive real number, and then you divide by the sum. So basically what ends up happening is the largest
Entry of the matrix or on a row?
on a row. So critically what you do is you have a probability distribution for each row that you get from softmax. So you get like a series of scores. You pass the scores through a softmax, and then you multiply that softmax matrix to basically take a convex combination of the value embeddings. So going back here, like this is the outcome of the softmax matrix, is this row stochastic matrix. Then you multiply that by the value embedding.
So softmax operation is stochastic. It's not a function.
It is.
It's no, it is a function. It's a deterministic function. Yeah. So it's different. Yeah.
Just make small.
Yeah. Yeah. It's a way of. Yeah. It's a continuous way of making a probability vector or making a vector.
The exponential thing is basically accentuating differences between them without actually taking the max. It just makes the max count much more.
Exactly.
That's what the role of the exponentiation is.
And a critical thing about the role of that exponentiation is that what you end up having is very often the result is that you will have the matrix will be approximately sparse. Mm-hmm. That a lot of the entries will be, one or a half or a third, and then everything else will be zero, because you're passing it through this exponential. So that's part of the reason why we're able to think in terms of like nice functions through this view is because you often have the fact that like the outcome of this is typically like either approximately low rank or approximately sparse.
I have another question.
Yes.
Why do you end up adding the original x? Like, what does that do?
Why do I add the x there?
Yeah.
Typically, it's more an optimization thing than it's like more of a stability thing. That often, if you don't add that, then like it will converge to something degenerate. There's some theoretical paper about, I can share you afterwards about it. But another way of thinking about it too is that like, you don't really want to like forget what your input is. Like it's good that, you have some list of words, and it's good to remember like what your root information is. And then you can do complex operations on top of that, but you at least don't have to like recreate the input on every level.
Okay, but it's going to be a different x on the next level.
Yes.
It's not the same x that gets carried on the way.
Right. Yeah. So, sorry, this is one unit, and then you layer them. Yeah. Good question. Yes.
Sorry, can I ask a question from the Zoom?
Yeah. I'll get to you in a sec. Yeah.
Sorry, I didn't see those hand up. Apologies. So I'm just curious. Your input is n cross d. The output is n cross m. But you're saying gx is x plus this. I feel like there's a dimension mismatch somewhere that I'm not getting.
Yeah. I'm for the sake of this talk, we should think of d and m being similar things, and possibly like maybe you have to pad x with a few extra zeros. I'm happy to take that one offline, but that's mostly just a notational convenience thing.
Thank you.
Yeah, thanks. Your question?
Yeah, are these parameters learned, or where do they come from?
Yes, so you'll learn the Q, K, and V matrices, and then you'll learn the multi-layer perceptrons. But the softmax, no parameters there, and like the overall structure is not learned. Yeah, good question. Great. Any other? This is a good time to ask any questions about uncertainties about the model. So yeah.
So the input there is an n by d, where d is the embedding dimension.
Yeah.
I thought that this took like tokens of text. So where does this input get embedded in the first place?
So there would typically be kind of like before the input, you'd have some mapping that like maps discrete tokens to embeddings. So you just learn like a table of like, this word maps to this vector. Yeah.
Sorry, so the MLP is for each token, right? For each embedding each token.
Yeah. So you have one fixed MLP that you apply to all the different embeddings. Cool. Anything else? Great. So then the next question I want to mention, which will be the subject of a lot of the remainder of the talk, is like, how do we think about these theoretically? You could think about them from the same universal approximation framework that we talked about before, but it's a little less satisfying because we're thinking about these as like variable input size models. It's harder to say what a notion of universal approximation is, or whether that's even the right type of behavior that we want to model. So there's a few different types of theoretical analogies that people have drawn to try to understand these. So one lens that people have worked on has been looking at them as recognizers of formal languages. So people look at languages such as Dyke languages of interlocking parentheses and trying to determine, they assess like how large of a transformer do you need to determine whether this actually belongs to that language or not. You have some papers that have formalized like here's a special family, here's like a particular family of regular languages that we can recognize, and outside this family we can't recognize everything. There are other papers that have looked at transformers and what they can do with automata. So maybe you have, you want to think about like composing different permutations, and then how do you do that using a model like this, and they've looked at how you do that efficiently. On the limitation side, there are other papers that have studied transformers through the lens of circuits, basically saying like if you have a transformer, you can simulate this using, if it's constant depth, you can simulate it with a TC0 circuit, and then we now know that because circuits can't solve certain problems, therefore transformers of that size also can't solve certain problems. Anna?
So this is, when you mean transformers as formal language recognition, do you mean transformers with learned parameters or with hardwired parameters?
Right now we're thinking about hardwired parameters. So most of the talk is going to be about expressivity. It's really hard to say anything about learnability. Like there are a few papers that try, but they basically, the only way you can really make progress is by looking at like very shallow models without the softmax, and you end up losing a lot of, I think, what is valuable about the model. Yes?
What's the difference between expressivity and learnability?
Expressivity is does there exist a network in this family of networks, like within the architecture, that solves a problem or computes a function? Learnability is given randomly sampled data from that function, can you learn it? And typically using gradient descent. Yes?
So in this talk in transformer, deep transformers, right?
Yeah, and actually, like, I had a previous paper where I was working on this and focused on the single layer model, and this is trying to like generalize that to deeper models. So the lens I'd previously worked on with both this paper and some previous things is framing transformers and communication protocols. And the rough intuition there is that, you have the model has the ability to do computation using the MLP layer, and it has the ability to send information back and forth using the attention layer, and maybe we can model it that way as like different agents that have information and they're able to communicate with one another in a restricted fashion. So bouncing off that great question, I had a previous paper before this that looked at single layer transformers and asked, are there problems you can do with deeper models that you can't do with one layer? Are there problems you can do with wider networks that you can't do with narrower networks? And you're able to do that by just like looking at communication complexity lower bounds. Like if you're familiar with, there are these like disjunctiveness or disjointness lower bounds that you could basically, you could make a reduction and prove the hardness based on that. And the issue is that it's very hard to scale that up to multiple layers of neural networks. So the goal of the work I'm talking about today is trying to figure out how to bridge that gap. I think I saw a question a minute ago. Is that?
I was just going to ask, I'm trying to understand what the circuit framing is and how that's different from the first two.
From which part?
I'm just trying to understand what the circuit framing was.
So the idea with the circuit framing is basically just that like all of these things, if you're dealing with like log precision numbers, can be simulated with some Boolean circuit. Some like threshold circuit or like arithmetic circuit. You can come up with one of those that will simulate the network. And one of the key issues there is that the class of circuits they look at is very coarse. So they'll basically say you can simulate this by some poly-n width circuit. But in this case, like, we don't want to think about, we ideally are not going to be going up to that capacity. Like we shouldn't be this shouldn't produce like a circuit of width like n to the sixth, but that's the only type of lower bounds we can import in. So it's a kind of like pessimistic view in that way.
I had a question, if you don't mind.
Yes.
From Zoom again. Can you go back to the previous slide for a second? Oh, this one. Yeah, this slide is fine, the one with the communication result. So if you think of the n agents as the entities that are, n inputs as the entities that are communicating, and so they each have, their d bits to communicate. Are you saying that the communication complexity bounds then put lower bounds on the number of parameters inside the transformer to do any communication? What does the actual result look like for the communication complexity?
Yes, so the result ends up being, I'm going to give you a task that you can solve with, that you can either solve with a two-layer neural network with very small width. So with an embedding dimension that would be like logarithmic in n. But that if I want to solve it with a one-layer neural network, I'm basically pushed out of the regime that I was talking about. Like n has to be, or the embedding dimension has to be roughly m, or has to be roughly n, which means basically you have to be able to like encode all the inputs in every embedding.
Right, so I guess I'm confusing two different notions of embedding that you alluded to, right? One is the embedding of the token, the dimension in which the token is embedded, but one is the width of the network, which I'm not sure makes sense for transformers in the same way as it does for sort of simpler neural networks.
Yeah, so I'm trying to avoid using the word width in part because like you kind of have two things you can think of almost as width. I'm thinking about the per token embedding.
Okay, thank you.
Yeah. Okay. So I'm going to change gears for a second. So if there are any other questions about transformers, I can take them now. Cool. So what is massively parallel computation? So this is a different MPC than the MPC that some of you might be familiar with. And I'll motivate it really quick with just like a very simple example of the parallel algorithm. So maybe you have some graph algorithm, like graph connectivity, and you can solve it in a sequential, you're given some graph, you want to determine whether it's connected or not. And you can solve it, sequentially using time growing, linearly in the number of vertices or edges, using a depth first search or something. But you could also solve it in parallel time in some ways if you think about like different machines possessing different nodes and being able to communicate with one another in a logarithmic number of rounds in the graph size. And like the rough idea I want to vaguely get at here is like maybe what you do is you have some graph, you color each vertex, and then you're able to do something where like you effectively like every round are going to kind of like agglomerate edges together. So like I'm going to look at my neighbors. If they're a different color than me, I'm going to share my color with them, so that eventually we get to the point where everything that is connected is either one color or the other. Everything that is connected shares the same color, and then you can just check, is everything the same color or not? And then by doing that, you're able to determine, using roughly log n rounds, whether a graph is connected. So like there's a parallel algorithm that works much better for solving this task. So why do I say this? Because we're going to look for a computational model of tasks that characterizes tasks of this form, and then we're going to relate that computational model to transformers. So the model I want to talk about is massively parallel computation, which is MPC. And this was developed by some people at the company I work at a long time ago. But this is I did this before I got the job. But it's a computational model of the MapReduce algorithm. And the idea that we want to think about is you have some very, very large input, and you have a very large number of machines, each with a lot of computational power, but with bounded memory. So we're going to take this large input, we're going to split it up among machines relatively arbitrarily, and then we're going to have a protocol where every round, each machine is going to perform some computation on its inputs, and then it's going to send and receive up to S bits of information. So this might sound a little similar to the way I was framing the transformer, and that is not coincidental. But the rough idea is that you want to think about the local memory being heavily restricted. So maybe I want to think about there being each machine having like n to the 0.01 memory if you have n size inputs. And then you have some global memory, which would be like S times Q. So maybe that's like n to the 1.1. So this is just a theoretical model. People can argue about whether it works or not. There's some case to be made that it does. But the key idea is that you have this like local computation on a machine, and then you have like a bounded capacity for how much information can be sent and received from a machine. So this model is pretty well studied theoretically. So for instance, there's a paper by Alex Andoni, a Columbia professor, and a few others in 2018, which characterizes MPC algorithms for graph connectivity as a function of the graph diameter. And it's basically able to validate the intuition I talked about before with the log n graph, or with the log n depth. That basically if I have a very small local memory per machine, and I have log n rounds and roughly n machines, there exists an algorithm that does this. People have put in the work and then used it to characterize a bunch of different types of graph algorithms. So the figure is a little bit small, but basically in each circle, like this is a collection of problems that are equivalent to graph connectivity in like a constant number of rounds. So basically, like if you have an MPC solution to graph connectivity, which you do, then you also have an MPC solution to minimum spanning forest, or planarity testing, or mincut, or graph bipartiteness. Like in some ways, you get all of these other algorithms for free, and you're able to kind of define this as sort of as a complexity class of sorts with this protocol. And this is I had a follow-up work that kind of explored this more for graph architectures. And then what you also have is you also have a pretty well accepted conjecture that this log n depth thing is just about the best you can get. That we have a log n algorithm to graph connectivity, and a bunch of theorists believe that the only way to beat log n is if you have like a very large, if you have either like linear local memory or you have super polynomial global memory. So again, I'm a newcomer to the field. I mostly do machine learning theory, but it seems like a lot of the theorists who are in this space believe this conjecture, so I'm going to choose to believe the conjecture. So this is, so we now have idea 1, which is transformers, idea 2, which is MPC, and then the core thrust of the paper that I worked on is trying to connect the two together. So roughly what we say is that there's a two-way relationship between the two models. So basically, like if I give you a transformer, you can simulate it using an MPC protocol. And if I give you an MPC protocol, you can simulate it using a transformer. And what that allows us to do is to basically import the results we already knew about MPC into the transformer world. So for instance, if I can simulate an MPC algorithm with a transformer, and I know MPC can solve graph connectivity, then I can effectively hard-code a transformer that can do graph connectivity. Anna?
Can I make a comment here? So it seems to me that one obstacle is just a purely technical obstacle was that you say that the individual processors can perform unbounded computation.
Yes.
And that would be hard to simulate.
That is a huge assumption, yes.
Yeah.
The reason I make the case that it's vaguely okay to do that is because if you look at a transformer, I don't have the numbers on hand, but there tend to be a very large fraction of the parameters that are used to parameterize the MLP. So maybe you can think that we are allowed to perform a lot of computation there. But it is an imperfect assumption, and I think one of the things that I would like to think about for follow-up works is like how you can better blend this with some of the circuit complexity literature. So what if you said like, MPC algorithms where the computation is involves like a bounded size circuit or something. Like it's easier to imagine importing that directly if you assume it that way. Anna?
My question is a little bit related. Like, why call it two-way relationship and not equivalence? Like, what's stopping you from calling it equivalence?
Because it's a little bit loose. It's loose. It's tight enough to get the bounds that I want out of it, but there's some looseness. We'll get to that in a minute, and that's another thing.
Wow. What?
Because you trained him well.
Sorry, I had a question on the Zoom, if that's okay.
Yeah.
One of the things that transformers do, if I'm not mistaken, is a sort of a certain amount of recurrent behavior where you can take the output from one state of transformer, you get a token, and you feed it back into the sequence as part of the next input. So there's a certain recurrent element which I don't know how important it is, but it seems to be part of the architectures. I feel like in your description of transformers and in the attempt to map on, you're going to have to drop that, or can you incorporate that recurrent element into this modeling?
There are ways of incorporating it. It is a little tricky because in some ways, like the rough way of thinking about it is like the recurrent element is kind of sequential computation. Like you can't simulate the parallel stuff using that, whereas the like layer-wise computation is more parallel. So I think there are ways to integrate the two. That's something I've been actively working a bit on. And there are some bounds you can show on how you can like mix the two well. But I think like for the sake of presentation, I think it's easier to think of this like for the sake of this talk is just a depth-wise composition rather than an autoregressive approach.
Okay.
Yes?
So a couple slides ago, you mentioned that there's like, okay, two parts to a transformer. There's a self-attention, which you duplicate across multiple channels, and that does the communication between each token and the same channel's sort of value.
Yeah.
And then you have the MLP, which is where each of the channels communicate between each other. So it's a parallel here that the communication layer of the parallel system is the MLP, and then the individual computation of each attention channel.
Exactly. Yeah. Communication in the attention, computation in the MLP. Yeah. Cool. Any others? Oh, yes.
In your MPC analogy, when those arrows like merge together in the next node, in the next like layer, right?
Mhm.
What is that? Is that like a user-defined function? How do you combine those inputs?
The way you should think about it is that the output of each like local computation is going to be basically like a collection of packets with like a message and a destination. And we're going to enforce the constraint that each machine can send at most S bits of memory, and it can receive at most S bits of total messages. So if you get more than, if you get more messages than your capacity, maybe the whole protocol fails. Yeah, good question. Great. So one key idea is that we draw this connection. We have this two-directional relationship carefully described. And then the critical thing, which I don't think I'm going to have time to get to today, is that we can also draw analogies between alternative architectures. So we can then say at the end that you can simulate this parallel regime using a transformer, but you can't simulate it using a recurrent neural network, or you can't simulate it using a graph neural network. Or a lot of these, like when I talked earlier about overcoming the quadratic time bottleneck, a lot of the approaches you'd use to approximate it are going to lose this core parallel computational property. So like you're gonna lose stuff pretty easily. So what I want to do is I want to give a brief overview of the proofs, and then I want to zoom out and talk a little bit about empirics to show that it's grounded in at least one like fairly straightforward real task that we can actually learn. So what do we show? Well, basically we have these two theorems. One way is transformers simulate MPC. The other is MPC simulates transformers, and that as a result gives us the corollaries that we just talked about. So for instance, then you have that a log depth transformer can solve graph connectivity, and that if you believe this previous conjecture I mentioned, that you need log depth. There's no faster way to do that unless you blow up the embedding dimension. So the first result is fairly straightforward. Basically, if you have an R-round MPC protocol, you're going to have some fixed local memory, and you're going to have some number of machines that's less than n. You can hard code a transformer with depth growing linearly in the number of rounds that's going to simulate this. And with the initial proof, you have a blow up you have like a 4-fold blow up in width, but it's not too big of a problem, and it's also something that we can actually reduce down using future work. So the key idea is, as was said over there, you simulate the local computation on the MLPs. You configure your keys, queries, and values so that the transformer is effectively like this. Effectively becomes a routing algorithm. So what you do is you encode like the sources and destinations of each message that the MPC unit is sending using the query and key vectors, and then you encode the actual message in the value vector. So now what you're able to do is basically you get the goal is to ensure that the softmax that the attention matrix that comes out of the softmax is going to have large entries. Like ij will be some large number if and only if element I is sending machine I is sending a message to machine j. And that message is so conveniently encoded in the value vector so that once you compute the average, it's there, and you can then carry on with the next round of computation. It gets a little more convoluted. Like you have to do some kind of fancy things to try to encode the value vectors just right. So there is some technical stuff. And then what I mentioned before is that as a follow-up work, we were able to get rid of this like 4-fold blow up in the exponent there. We're able to say like for some small epsilon, you can do it by scaling up the algorithm. The architecture is size at most like poly 1 over epsilon. So if we think of epsilon as like some very small number, we can get this effectively for free without the blow up before. And what this gives us is this allows us to directly import in some of the algorithms we talked about before. So we have an algorithm for graph connectivity using log n rounds of communication. We also have one that works for log n layers. And before we knew from MPC that you can do that using a small local memory, which means you also then have a small embedding dimension. So you're able to translate things that way. Now for the other direction, what you have instead is you're basically able to show a similar thing with the big caveat that there is a blow up in the number of machines. So the lack of equivalence is that basically you're going to sharply increase the amount of global memory in order to simulate this. And this is a gap that I've tried to bridge. I have not been able to. I want to keep thinking about it. I'm not sure if you can bridge it. I think it might just be the case that MPC is not the perfect analogy for transformers, even if it's a decent one. But the idea is fairly straightforward. You have machines for each embedding vector. You have machines for each inner product, which is a total of n squared machines. And then you're able to kind of communicate using this like regimented way, using standard primitives from the MPC regime. And even though it's not tight, it's still tight enough to import in the conjecture I mentioned before. So if you believe the conjecture, even with the loose reduction, you still have that our graph connectivity construction is optimal, and that log depth is the best you can get for small embedding dimension. So any questions about these two kind of main results? Yeah.
Do you have like open source code application for this kind of?
I have. So primarily it's theory works. There's no immediate application, but I do have some like tasks that we trained it on that we can use to demonstrate that you get this type of trade-off. Yeah. Question back there? Oh, question on Zoom.
Sorry, yeah, I got it. Since the MPC units are all essentially streaming processors, right, because of the limited memory, and you're doing a lot of matrix calculations, I suspect that there's some kind of, not too complicated correlate to say that you can approximate the resulting matrix in a transformer without needing the n squared computation, as long as you're willing to use some standard techniques to sort of do approximate calculation of the inner products. I mean, I'm not sure how interesting it is, but I'm curious if there's because you mentioned some approximation results earlier on. I'm curious if you've looked into that here.
So I've tried to do it using approximations, and I think there are theoretical results that suggest that it would be very hard to do using fewer than n squared machines. I kind of want to take it offline, so I think it's a bigger conversation. But like,
Okay.
I can send you some papers because I think it's a hard thing to overcome.
Okay, thanks.
You stole the question, right? Yeah.
So is the reason this is you do this approach? So like I guess another thing you could do is you could say this is the algorithm that makes the transformer. Can we implement such proofs for graph connectivity in that lens, right? But maybe that's hard, and so it's easier to make a two-way relationship with this and MPC, which has like work is already proven.
Yeah.
As far as that, why we should.
Yeah, I mean, a lot of like the motivation of this is like laziness. You know, it's like I don't know how to define a new parallel computational model. I'm not an expert in that area. It's easy. It's like more feasible as a learning theorist for me to say like, let me find this really rich existing literature and see how I can apply that to my work. I think there is certainly a more apt parallel computational model to transformers than MPC. I'm just not sure that like I'm going to be the one to define it. Cool. So I have a few more minutes. So what I want to do is I want to talk very briefly about empirics, because some of the examples here are kind of weird, and I want to ground this in like a somewhat simpler sequential task that you could actually train transformers on, and we did actually train transformers on. So as a quick show of hands, has anyone heard of induction heads? Okay, so a few people. So the induction heads is a task that was defined by some people at Anthropic, and it's a simple like sequential analysis task where basically I give you a collection of tokens. I'm just going to ask you to find the last time a token occurred and then copy forward what came after it. So in some ways, like it's a natural way of predicting what token might come next. So in this case, I give you the sequence of tokens. It ends with an A. I find the last time A occurred, and then lo and behold, that's B, and then therefore I output B for this. So like this is a simple task that they defined. It's both doubly cool because like it's a thing that they find that actually shows up in trained models. Like this is like a unit that models learn without being trained explicitly to do so. And also it like showcases like the importance of depth in transformers. So from a theoretical lens, there's a paper written by Alberto Bietti, who's one of my friends and collaborators, which shows there's a natural construction for doing this with 2 layers. You can learn this construction. And critically, there's a follow-up that I did with my advisor Daniel and Matus that shows that it's impossible to do this with 1 layer by using the same communication complexity approaches. So this is one task. We can then generalize it a bit and say, okay, what if we want this to be, instead of a 2-step reasoning task, a k-step reasoning task, where you're basically trying to follow a certain number of pointers. So like in this case, what the 2-hop induction heads is going to say, let me find the last time A occurs, let me find what comes after that, let me find the last time that occurs, and then find that. So you're doing multiple jumps. It's just like a simple way of writing down some task of basically like following pointers, where in this case the pointers are these relationships. And you can generalize it to go as many times as you want. And what we're able to do is, one, we're able to import in basically all the theory results we talked about before. So there is a natural log n depth construction. 2, we can show that depth is conditionally optimal based on the same corollary, or based on the same conjecture we talked about before, by basically embedding a graph connectivity problem in one of these. And then we're also able to show the same separation from other architectures, which means that like critically, if you think of this as like an important type of multi-step reasoning task that a model should be able to do, you lose out on that if you do a lot of these subquadratic approximations, or if you use like a recurrent network. So I'm going to skip the construction for now. It's something you can do. It's cool. But I want to also say that I actually trained some models. I trained some GPT-2 style models, so it's fairly small. I trained it on this laptop before I worked at Google. And what we did was we did this pretty directly. So I generated synthetic data using this distribution. We trained a variety of depths. And what we found is that basically we get kind of the sharp learnability threshold that we would expect. So if you see in this plot, the black one represents the depth 2 network as we increase the complexity of this task. And what this tells us is that it does great on 1 hop, and then it falls apart. The depth 3 model does well on 1 hop and 2 hop, and then it gets bad. the 4-hop, same for 1 through 4, and then it gets bad. So what we're noticing is that like this logarithmic construction that we have and this logarithmic lower bound that we suggested actually seems to be the case. And then we also did some interpretability analysis where we basically showed that like the individual tension units are actually doing what we expect them to be doing. So like we write down a construction where you're basically like passing along these like linkages from one to another. And we're able to show that like when we train models in a synthetic environment, we reconstruct something that's very similar. So I don't think I'm gonna have time to fully go through this, but if anyone wants to talk about this stuff after the talk or in any other capacity, let me know, because there's, it was a very cool, I really enjoyed working on this, and like I think I was surprised by how well it worked. Like I didn't expect this to be actually learnable. I think because the talk because we talked a lot, I'm not going to talk so much about this, but this is basically talking about some other theory, which was how we can look at the other architectures and show that they can't solve this type of problem. So this is those subquadratic models. So yeah, there are a lot of steps forward, kind of based on the questions we talked about today. So looking at different types of models, can we reanalyze this arbitrary MLP assumption and do something better with circuits maybe? And can we better understand, can we fix this gap between the two directions to reduction? And then I think there's also, I mentioned, this is one theoretical lens. There are others as well. And I think there's a lot of opportunity to integrate these different lenses. So thank you, everyone, for joining. And I imagine we can keep taking questions if people are here, either here or offline. And I'm also here today until like 6 or so. So if people want to chat, just talk to me or send me a message or what have you.